I am Tianyang Luo from Peking University. Today I will present Diamond, our work on dynamic inference for Adaptive Edge MoE using a heterogeneous in-NAND and near-DRAM compute architecture. The key message is that Edge MoE inference should not treat NAND flash as passive storage. With the right architecture, mapping, and routing support, NAND can become the main compute substrate for expert VMMs, while DRAM handles the dynamic runtime state. Here is the outline. I will first motivate why Edge MoE inference is a memory system problem. Then I will describe the Diamond architecture, our mask-based in-NAND VMM and mapping method, the adaptive expert selection method, and finally, the evaluation results. Let me start with the background and motivation. Edge LLM inference is interactive and token by token. In this setting, the batch size is usually close to 1, so weight reuse is very limited. Every new token repeatedly touches a large number of model weights. As a result, the bottleneck shifts from raw compute throughput to data movement. Since decode time transformer computation is dominated by a vector matrix modification, moving weights becomes the dominant source of latency and energy. MoE specifies computation, but it makes the memory problem even more severe. Only a subset of experts is selected for each token, but all expert weights still need to be stored somewhere. The total parameter size can be several times larger than the selected parameters. NAND flash is therefore attractive because it provides the required storage capacity for model weights. However, NAND alone is not sufficient. Its low endurance makes frequent updates unsuitable, while self-attention requires dynamic storage for KB cache. This motivates adding a DRAM side module for dynamic runtime state. The next question is whether we can simply use the SSD or near-NAND computing. For MoE, selected experts are determined online, so expert weights need on-demand loading. DRAM to NPU loading can already exceed compute latency, and SSD to DRAM transfer adds even more delay. Near-NAND computing reduces off-chip transfer, but it is still limited by page readout and provides only limited throughput per die. In-NAND computing directly uses array-level parallelism for VMM and can use compute capacity to hundreds or over 1,000 jobs per die. However, in-NAND computing is not automatically a perfect fit. The physical VMM granularity is fixed by the NAND array. Input parallelism is kept by TSG activation, ADC precision, and analog non-identities, while output dimensions follow the number of bit lines. MoE layers, on the other hand, expose diverse projection shapes and dynamic expert combinations. A pool mapping either wastes NAND capacity or increases VMM latency. This mismatch motivates our mask-based VMM and mapping design. In this work, Diamond addresses these challenges in 3 steps. First, it uses a heterogeneous in-NAND and near-DRAM architecture. In-NAND handles static VMM weights, while near-DRAM handles dynamic state and attention. Second, mask-based computing and mapping improve VMM efficiency without sacrificing storage. Third, adaptive expert selection resolves runtime expert conflicts with limited routing deviation. End-to-end, Diamond reaches 197.3 tokens per second and 5.8 tokens per joule on Mixtral 8x7b. Now, I will move to the Diamond architecture. Diamond follows the general structure of an SSD with a controller and NAND dies, but turns each memory level into a compute-compatible component. The in-NAND modules accelerate large static VMMs and dynamic experts in place. The near-DRAM module stores KB cache and executes attention and SFU-heavy operations. These modules are integrated through a 2.5D package to provide high bandwidth between NAND packages and near-DRAM logic. Inside each NAND package, 8 NAND dies are stacked with a control die and vertical links. Weights are stored in SLC mode, and replicated across dies so that int8 VMM can be processed bit parallel. The array itself is largely unchanged. The main additions are peripheral ADC, shift and add logic to convert bitline currents into digital partial sums. We evaluate input parallelism at 512, 1024, and 2048 TSGs. The Near-DRAM module provides high-bandwidth local storage for runtime data. It consists of 4 DRAM layers with 2x2 tiles per layer, providing 1.5 GB capacity and 1620 GB per second bandwidth. The bottom logic die is organized to match the DRAM tile structure. It includes P arrays, SRAM buffers, I/O control, and special function units, providing 2 TOPS int8 compute for VMM and special functions that are better suited for DRAM tie. Since in-NAND computing is analog current domain computation, we explicitly consider reliability. The read strategy is optimized to suppress cell-level variation. Saturation region sensing reduces VTH sensitive current fluctuation, and current clamping further limits read current to improve max stability and power efficiency. We also match ADC precision to actual MAC distributions across 512, 1025, and 2048 input parallelism. 7-bit ADC resolution is sufficient to preserve inference accuracy with negligible degradation. At the operator level, partitioning follows access pattern and update behavior. In-NAND computing handles large static VMMs, including most projections and dynamic experts. Near-DRAMs handles frequently update KV cache and shared experts. For QKV attention, WQ is placed near DRAM, so attention can start early, while NAND computes K and V projections in parallel. Next, I will explain the mask-based in-NAND VMM design. Without mask, some operation unit combinations cannot be read together without activating unselected data. Diamond uses the vertical dimension of 3D NAND as a gating layer. A mask cell and a wait cell are placed along the same string, and the series connected cells implement a logical AND. Mask 1 enables the corresponding OU to contribute to the bitline current, while mask 0 blocks unselected OUs without moving or rewriting weights. Mask patterns divide operation units into non-conflicting groups. Diagonal and anti-diagonal patterns activate OUs with distinct input and output ports, and circulant shifts cover the full OU array across multiple read cycles. The key benefit is that dense storage is preserved while read cycles are reduced. In this example, a 4x4 OU array is covered in 4 reads instead of 16 sequential reads. The mask generation method also supports different OU array shapes. Square arrays shows diagonal and anti-diagonal masks directly. For rectangular arrays, we normalize the shape before mask reconstruction. These mask patterns are then translated into actual deployment decisions. Now I will move to the dynamic inference for MoE, especially the adaptive expert selection. The router selects experts based on model-side routing scores. However, the original top K decision does not consider NAND placement or mask compatibility. This creates runtime hardware conflicts. Selected experts may share output ports, causing invalid simultaneous activation, or they may lack a common valid mask pattern, forcing extra read cycles. AES adjusts the selected expert set according to disk hardware constraints. AES begins by preserving the router's preference as much as possible. Experts are scanned in descending routing score order, and highest score expert is selected first as the anchor. This keeps the algorithm close to the original model decision instead of replacing the router entirely. Next, AES checks hardware compatibility during selection. The second and third highest scoring experts are considered one by one. Each candidate is accepted only when it can be activated under valid NAND mask constraints, together with the already selected experts. When the fourth and fifth highest scoring experts conflict with the current selected set, AES temporarily skips them. The important point is that these experts are not immediately accepted just because their routing scores are high. On the other hand, hardware compatibility becomes an online constraint on expert selection. AES then scans lower score experts for the nearest compatible alternative. In this example, it substitutes E1 for E5. The substitution is accepted only when the score difference between conflicting experts and the compatible alternative is below threshold T. This bounds the deviation from the original top K routing while improving in-NAND parallelism. To avoid making AES a new latency bottleneck, we implemented it with a lightweight dynamic mask selector. Now I will present the evaluation results. We evaluate Diamond under 3 input parallelism configurations. Diamond L, M, and H corresponds to 512, 1024, and 2048 input parallelism. All configurations use the same hardware substrate. Our baseline includes GPU and memory-centric ASIC accelerators. AES uses the threshold T to avoid overly aggressive changes to the router decision. A smaller threshold keeps the selected expert set closer to the original top K routing, while a larger threshold gives AES more freedom to resolve hardware conflicts. We use expert similarity and pairwise difference to quantify this routing perturbation. With the selected T, AES consistently limits the deviation across models and datasets while still reducing hardware conflicts and keeping the accuracy close to the original top K routing. The ablation results show that both mask design and AES are unnecessary. Mask design improves static in-NAND resource utilization by enabling more legal parallel reads under dense storage. AES further decreases runtime conflicts caused by dynamic routing. Together, they improve decode speed, and conflict ratio is mostly reduced to 0 after AES. For end-to-end decode speed, the improvement mainly comes from executing expert VMMs in place inside NAND arrays and exposing more usable parallelism by mask and AES. On mixture 8x7b, Diamond reaches 197.3 tokens per second. Across models, it achieves large speed ups over GPU and edge ASIC baselines. Energy efficiency reflects a throughput power trade-off. On mixture 8x7b, Diamond reaches 5.8 tokens per joule. It avoids off-chip weight movement and amortizes NAND array activation overhead across many MAC operations. At the same time, larger input parallelism activates more cells and increases unused baseline current, so the best energy efficiency point is not always the highest throughput configuration. Finally, I will conclude the talk. To conclude, Diamond integrates in-NAND and near-DRAM computing to support MoE inference on edge devices. The heterogeneous architecture addresses high storage, high bandwidth, and diverse data access requirements. Mask-based computing addresses the mismatch between diverse VMM shapes and fixed NAND granularity, enabling efficient and flexible MoE mapping. Adaptive expert selection further addresses runtime expert conflicts with lightweight hardware support to keep online decisions overhead low. Overall, Diamond achieves 197.3 tokens per second and 5.8 tokens per joule on mixture 8x7b, showing the benefit of architecture, mapping, and routing code decision. Thank you for your attention. If you are interested in more details, please refer to our paper. Thank you.